Okay, so any questions before we get started? Today we're going to finish chapter 12, which is actually the very last chapter for your midterm 1. Okay. So any questions before we get started? So I hope everybody follow along without a problem. Okay, if you do, really, you don't have like almost 2 weeks left. No, 1.5 weeks left at most. Okay, so if you need help, reaching out as soon as possible. But like I say, the most important thing is actually to understand the things I have told so far. Okay, and next week we are going to review chapter 10 to 12. Then we'll just quickly go through the important concept that you should know. And then we actually do a lot more practice. Okay, we're going to go through, I don't know, 15, 20 questions in the in-person lecture. Okay, so if you can actually went through all the things that we have so far, okay, and trying to follow along next week, okay. If you can really feel like I have no problem follow along, and I can really get all the numbers by myself using my calculators, then you are more or less ready for midterm 1, okay. So if there's actually no more questions, should we get started? Okay, so on Tuesday, we start to tell you something that's very simple, right? We define what is chemical quotient Q and what's the difference between Q and the equilibrium constant K, right? So I think in the previous presentation, we start to think about how things actually evolve from the beginning all the way to the equilibrium, right? So for all the chemical reaction, the final destination will always be the equilibrium, okay? And we're going to elaborate that concept a little bit more today, do more calculations based on the description, okay? So 2 things we want to actually talk about today. One is called the ice table. How many of you have heard of this term, ice table, in the past? Okay, so if I feel like there's not many of you actually heard of this. Okay, so the I stands for initial, change, and equilibrium. Okay, so every time when we do the question in these chapters, you will need to recognize which state you are at. Okay, either you are at the initial stage, change stage, or the equilibrium stage. Okay, another very important concept that we should actually have is every time when we want to do the calculation, we'll always use equilibrium constant, okay? That means you can only plug the numbers when it is at equilibrium, okay, to calculate the quantity you want to calculate. Okay, and this thing will become more clear when you go through the examples. Okay, so that will be actually our first focus. Okay. After we finish that, then we're going to talk about another very interesting concept called the Le Chatelet principle. Okay, so what that principle does is that, let's say my system right now is at equilibrium. Okay, if I do some changes to my system, either I change my reactant concentration or product concentration, okay, and how can we actually predict the reaction is going to move? Okay, so let's actually the things that I want to learn for the Le Chatelet principle. Okay, and the things that can really change the equilibrium, including the reactant concentration, or if it's the gas phase, the pressure of the reactant or product. Okay, the temperature will matters if your reaction is either endothermic or exothermic. Okay, so those are the things that's relevant. Okay, so that's pretty much all the things we want to talk about today. Let's start from the very simple one. The ice table. So the I stands for initial state. This is actually a change that's going to happen before you reach equilibrium. Okay, so it is critically important that you recognize the process. Okay, so every time when we talk about reactions, okay, I give you some information in the very beginning. Okay, then you should know that, okay, whatever condition you are given, eventually you will undergo some changes and then eventually reach equilibrium. Okay, so these three stages, they are distinct different stages that you must recognize the number you were given belongs to which one. Okay, so let's actually main task today. Okay, so how do you know the things is actually at the initial? Okay, so typically you're looking for a few keywords. Things like this. Okay, if you see in your question says they give you like 3 more of A, 2 more of B, they will mix together, okay, or they will put together, okay, or they're actually allowed to react, okay. Things like that tells you whatever number I give you that belongs to your initial state, okay. Whatever number you have in the initial state, you cannot put it plug into your equilibrium constant equation. Okay, so that's actually something that you must know. Okay, otherwise just put the wrong things into the equation. Okay, the equilibrium constant is only useful when the number that you're given belongs to your equilibrium state. Okay, so that's actually the first thing that you need to know. And how do you know the things is actually belongs to the change? Okay, typically you're going to see the word like increase or decrease by certain amount. Okay, so that actually tells you those are the changes. Okay, so those are the keywords. Okay, once you see, okay, the compound A is increased by 3 moles, for example. Okay, then you know that 3 is actually belongs to the changes, not the initial, not the equilibrium, it's actually the changes. Okay, and the very last one, how do we know things is actually an equilibrium? It will actually really tells you these things is actually at equilibrium, okay? Or it will say equilibrate. Okay, so those are the keywords that you know. The number that you have belongs to the equilibrium state. And those are the number, and only those number can be plugged into your equilibrium constant for calculations. All right, is that clear? Any questions for this? Okay, let's do some practice. Okay, so this question says at 700K, the reaction below has a Kp value of 54. An equilibrium mixture at this temperature was found to contain 0.5 atm each of H2 and I2. Calculate the pressure of HI at equilibrium. Okay, so let us actually the questions. What's the keyword here? Yes. You see the keyword equilibrium, right? That tells you the number of like 0.5 atm H2, 0.5 atm I2 that belongs to the equilibrium state. Okay, it's not initial, it's not a change, it's actually the equilibrium state. Okay, so what's the things you want to calculate? What's your Q? If you read the question again, what's your Q? The pressure of HI at equilibrium. Yes, label your states, it's very important. Let's prevent all the confusions. Okay, so I will write the pressure of HI at equilibrium. Okay, I use EQ to represent equilibrium. All right? Okay, so you know what the Q is, right? Then let's look what the data that you have. The equation, of course, is H2 gas form plus I2 gas form. That give you 2HI in the gas form, right? So once you write out the equation, you should know, since everything is going to express in terms of gas, right? So you have Kp, right? It's not a solution, it's actually a gas. Therefore, I express everything in terms of pressure. That's why I write Kp instead of Kc. Okay? So how do you actually write out the equation for your Kp? Then you must know that this will be the pressure of your H2, so Hi at equilibrium square, the pressure of your H2 at equilibrium times the pressure of your I2 at equilibrium, right? And then from the question, you know, this value is going to equals to 54, right? So let's actually the things that you can write out first. Okay. Okay, so this is just for to help you to actually think about, okay, where the number should present. Okay, so we are going to do this ICE table practice for this chapter. Okay, so you know why sometimes you can use the number, sometimes you cannot use the number directly. Okay, so here it says you have 0.5 atm each of H2 and I2 at equilibrium, right? Therefore, I should put the 0.5 right here and the 0.5 right here. Everybody follow this? Everybody smile with this? Okay, make sure that you know where to put that 0.5, okay? And then the things that you want to solve is this, right? Pressure of HI at equilibrium, okay? You must know the position of that guy, okay? Because only the things that you roll for this specific roll can be plugged into these specific equations, right? So, then you know your Kp will equals to the pressure of your Hi at equilibrium square over the pressure of H2 is 0.5. The pressure of your I2 is 0.5. And this whole term will equals to 54. Okay, therefore, you know the pressure of your Hi at equilibrium square will equals to 54 times 0.5 times 0.5, right? And then to solve your just the pressure of Hi, then you take the square root of that. And then once you do that, you will be able to get a number of 3.68. Okay, so the pressure of your Hi at equilibrium will equals to less specific number. Okay. So any questions for these questions? Okay, it's very straightforward, right? But the key is that if you can see, if you can set up that equation right, okay, if you can put the number at the correct rows, and then you recognize only the rows in the equilibrium row can be used to plug into your KEQ, okay, then you can calculate these things very easily. Okay, so things will be actually a little bit more complicated when we go to the next questions. But before we do that, everybody follow this? Good. Okay, so now we want to have some slightly more complicated questions. Okay, so if you read these questions, it says, at a given temperature, 2 atm of H2, 1 atm of I2 are mixed and allowed to come to equilibrium. The equilibrium pressure of HI is found to be 1 atm. Calculate Kp for the reaction at this temperature. Okay, so these are actually the questions that confuse students so much. Okay, what are the keywords here? There are actually many keywords, okay? So first, if you see this capital K, P, tells you this is chapter 12 questions, right? You must use equilibrium constant. Okay, what are the keywords? Other keywords. Mix and allow to come to equilibrium, right? So that means actually the number that given here, this and that. What are their status? Initial. Okay, it's very important you see that. Okay. And what's the things that we want to calculate? KP, right? So if you read these questions, okay, then you actually see that the things that you want to have is actually KP. Okay, you want to calculate this. Okay, so if you write out the equation, this is basically exactly the same equation we just wrote from the previous, it's the same as the previous questions, right? Therefore, you know the KP was defined as the pressure of your HI at equilibrium square over the pressure of H2 times pressure of I2 both at equilibrium, right? So you know that's actually the things that you want to calculate. Okay. To calculate your KP, that means actually you need to know the pressure of H2, pressure of I2, and pressure of HI at equilibrium. Okay, so that's the things that you must know. Okay. Then you can just set up your ice table, right? So where should I put 2 and 1? At the initial row, right? So 2 will be for your H2, right? 1 for your I2, right? What else? That's actually another thing, right? This sentence. Where should I put that 1 for the HI? Which row? Equilibrium row, right? That means actually it should show up here. Do you see that? Okay, that's how you actually set up your data. Okay? Everybody fine with this? Okay, then how do we actually go from this data, okay, to figure out this, that, so you can actually plug everything in to get your KP. Okay, so that's the plan, right? You need to actually figure out what those two numbers at equilibrium first. Okay, so what's the clue? So here, apparently, you need to actually figure out, okay, the changes. Okay, so when the reactions start to happen, okay, that means actually your reactant is going to start to decrease, right? Your product is going to increase, right? So it will decrease by a certain amount, increase by a certain amount. Okay, so now it's actually a time that you need to figure out, okay, what that amount is. Okay, so let's say your H2 decreased by X moles. Okay, then how much more of your I2 will decrease? I hope you know you should put negative X here, right? Because how do you know it's actually the same? Because the coefficient is 1 to 1, right? That means you will consume 1 mole of H2 with exactly 1 mole of I2 to produce how many more of your product? 2 moles, right? Therefore, you know, in your change will be this, right? Okay, so everybody understand why I put negative for my reactant, positive for my product? Because the reactant is consumed, right? It's going to decrease from the initial. That's why I put negative X. For the product side, it's increased, right? That's why I put plus. And the reason I put 2 is because you know 1 mole of reactant plus 1 mole of reactant going to give you 2 moles of product, right? So it's really simply due to this coefficient, right? This coefficient. 1 to 2. That's why I put 2, right? If today I change this to 5, okay, let's say you have 1H2 plus 2I2. Let's just do another practice. I use different color so you can see the things. Okay, let's just do some crazy number. Let's say it's this. Okay, 2H2 plus 3I2, that give you 5HI, right? So if that is actually the case, then if I put negative 2x for my H2, then the second term will be what? Negative 3x. And then for the product will be positive. Okay, so you must know that, okay? I feel like I make the coefficient kind of like, okay, let's do 1 here. Then this one will be negative 1x. Okay, the second one will be negative 3x. And then for the product will be positive 5x. Okay, so make sure you know the reason you write all those coefficients simply because your equation have those coefficients. Okay, so get back to this question again. Let's solve this. Okay, so once we write out all these things, one thing that you should know, how do we actually come to equilibrium? It is actually if you add the number of your initial plus the changes that give you the equilibrium, right? So basically the first row, if you're adding up, then you get the third row. Okay. But when we're trying to do that, then you'll see some problem because what's the value for this guy? What's the value for that guy? 0, right? How do you know it's actually 0? Because in the beginning, all you have is reactant, right? It says you put the reactant in, okay, and allow them to react, right? Allow them to come to equilibrium. That means actually at the time, in the very beginning, do you have any of your product? You don't, okay? Therefore, you should know. Based on the description, you should know there should be 0 here, okay? And then we know I plus C will give you E. Okay, that means actually, if you do this, I want to focus on the things that you have here. From here, you know, 0 plus 2x going to equals to 1, right? From here, what can you do? You can actually calculate your x, right? So your x will equals to 1 over 2, which is 0.5, right? So if you know your x is actually 0.5, therefore you know here is actually minus 0.5. This is actually minus 0.5, right? Then you can calculate the pressure of your H2 at equilibrium should equals to 2 minus x, which is 2 minus 0.5. It will be equals to 1.5, right? Therefore, you should put 1.5 right here. The pressure of your I2 at equilibrium will equals to 1 minus x, which is 1 minus 0.5. That will equals 2.5. Therefore, you know you put 0.5 here. Okay? So far, so good? Okay. So now, do you see that you have all the numbers for everybody at the equilibrium row, right? Since you have everybody, then you can start to write out your Kp. It's going to equals to the equilibrium pressure of your Hi, which is 1 squared, over the pressure of your H2, 1.5, pressure of your I2, 0.5. And that will give you a value of 1.333. Okay? And that will be the answer. Okay? I hope this is actually straightforward for you. Okay? But this will only be straightforward that you have, if you have very concrete understanding that only the number at the equilibrium row can be used to compute your equilibrium constant. Okay, so once you understand all this, I want to actually review the questions again. And ask yourself, if you don't have these structures that I just wrote, if you don't have a correct understanding of initial, change, and equilibrium, you should see that the question is actually very confusing. Right? So that's the things I want you to see, because one thing that students did not do well enough for CHEM2 is actually you guys ignore the importance of reading the question carefully and fit the content of your question into the proper context. Okay, so having all this structure is critically important for you to solve very complicated questions. If you have this in mind, okay, if you have this structure in mind, you'll find all the questions in this chapter. It's actually very simple. Okay, all you want to actually make sure you do is actually read the question carefully, play into the correct roles. Okay, then the calculation will be actually become very apparent to you. All right, I hope this actually gives you a better idea about what you're going to encounter when you do your homework and quiz. All right, so let's do one more practice. But before we do that, any questions for this? Everybody follow this logic? Okay, so here says in the reaction below, 0.5 ATM each for H2 and Br2 were placed into 1 liter of flax and allowed to react. Given the Kc equals to 4, calculate the equilibrium pressure of HBr. Okay, so again, every time you see Kc, Kp, right, you know it's actually chapter 12 type questions, right? And then another keyword here, right? Will place into and allowed to react or allowed to reach equilibrium, right? It tells you whatever number I see here belongs to which row? Initial row, right? See, it becomes very simple. If you can actually recognize the keywords, okay, you feel like, oh, the question is just so easy to solve, right? Since it's given you the initial, right? And then it gives you the Kc, that means actually you must use your ICE table, right? List out the initials, make sure you know the changes, right? And then really calculate what's the final value you should have that can populate in your equilibrium row, okay? Then use that to calculate the ratio of HBr, right? So those are the things that you should have before you actually even get started, okay? But once you know that, then you can just go back to our QD pack again, right? The Q is what? What's the things you need to recalculate is the pressure of HBr at equilibrium, right? So that's actually the target. Okay. Data, write out your equation first. H2 gas plus Br2 gas. They give you 2 HBr gas, right? And then you can put the ICE. Okay. And then you should put 0.5 of H2 and Br2 in the first row, right? So you should put 0.5 here, 0.5 here. Okay, and then it says Kc equals to 4. Okay. If you look at this equation, should you have Kc or Kp? Kp, right? Because all the things that you have, they belongs to the gas, right? Therefore, you know, in order to do all the calculation, you must have Kp, right? Then there should be pressure of your HBr square, pressure of your H2 first power at equilibrium. If you see this, okay, I will start to skip that equilibrium sign now, okay? The pressure of your Br2, right? So let's actually the things that you should have. But do you have Kp in this case? You don't, right? What do you have? Kc. Do you know how to convert the Kp to Kc? Okay, so this actually goes back to the things we actually discussed on Tuesday's lecture. Okay. Okay, so this is why on Tuesday I actually intentionally list this out the conversion between Kp and Kc here. Okay, Kp is equal to Kc times RT to the delta n's power, where the delta n is actually the mole of the gas on the product side, subtract the mole of gas on the reactant side. Okay, so how do you actually memorize this? How do you know it's actually Kp equal to Kc times RT to the delta n's power? Okay, so the way you should memorize is this. Everybody understand this, right? PV equals to MRT. What's this? Ideal gas law, right? So if you move the V on to the other side, you have P equals to N over V times R times T, right? What's this? That's a concentration, right? That's the molarity definition, right? So you know. Okay? So P will give you Kp, right? C will give you Kc times RT. Okay, now it's actually the delta N. Okay, so you want to calculate how many of that? You want to calculate, okay, what is actually the differences between the gas molecule on both sides? Okay, so, and the delta N was calculated actually very simple, right? So you just calculate how many mole of gas molecule you have on the product side minus mole of gas molecule on your reactant side. Okay, so that's actually how you do the conversion. So with that in mind, let's look at this equation. What's your delta N for this specific chemical reactions? How many gas molecules you have on the product side? 2, right? How many of gas molecules you have on the reactant side? 2, right? So what's your delta N? 0, right? So therefore you know delta N is equal to 0, right? Therefore Kp is going to equal to Kc times RT to the 0th power. Okay? Therefore you know anything to the 0th power give you value of 1, right? So in this case, your Kp is going to equal to your Kc simply equals to 4. Okay? Everybody fine with this? Any questions for this? No? You never consider what if condition, huh? What if the delta N is actually not 0? Yes, you need to actually know your temperature. You need to know your R, right? Which R? 0.082, right? Because it starts to involve gas. Okay, you need to know your temperature. Okay, so you need to plug in those numbers. Okay, then see whatever delta N number is, you just calculate that using your calculator. Okay, then you'll get the corresponding Kp value. Is that clear? Okay. So in this case, it's easier, right? Because you know your Kc and Kp are actually the same. It's equal to 4, right? Okay. Then what? This is not useful, right? Because that's not something you can just plug into your equilibrium constant. Okay. So you want to actually somehow figure out what this is, right? In order to go from initial to the equilibrium, you must use your changes, right? So then you need to start to assume for your reactant, you're going to decrease by X mole, okay? For your H2, then this one will be negative X as well, right? Because the ratio is 1 to 1. And this one will be plus 2X, okay? Therefore, you know once you reach equilibrium will be 0.5 minus X, 0.5 minus X. This will be 2X, right? Okay, so once you know that, then you know your Kp, which is going to equals to 2X squared divided by 0.5 minus X, 0.5 minus X, right? So it will become 2X 0.5 minus X square, and these things will equals to 4. Okay, then you take the square root on both sides. Then you have 2X over 0.5 minus X is going to equals to square root of 4, which is equals to 2. Then you expand on both sides. 2X is going to equals to 2 times 0.5 minus X. So 2X equals to 1 minus 2X. So 4X equals to 1, X equals to 0.25. Okay? So once you figure out X equals to 0.25, you should notice that the X is actually not the things you want to provide, right? That's not the things you want to solve. You want to solve this. The pressure of HBr at equilibrium, right? Which is this term, right? So since you know the value of X, therefore you know the pressure of your HBr at equilibrium should equals to 2X, which is 2 times 0.25. Then you should get the value of 0.5 ATN. Okay, so that's actually how you come to that final answer. Okay, so any questions for these 3 problems that we went through? Okay, so I want to re-emphasize that only the number in the equilibrium rule can be used. Oh yeah, sorry. You mean the Kp, the things I wrote in the very beginning? Just want to make sure I understand your question correctly. This guy, how do I get this? So that's actually the things we went through in the very beginning of the class, right? So we introduced you the most famous chemical reaction, right? AA plus BB give you CC plus DD, right? So the way you write out the chemical quotient Q is put the product on the numerator, right? So C to the C's power, D to the D's power. Reaction on the denominator, A to the A's power, B to the B's power. That's the definition of chemical quotient, right? And then when this system actually reach equilibrium, you can still use the same equation, but the Q now become your K because right now you're at equilibrium. Okay, that's actually how I get that equation, the equilibrium constant equation from the very beginning. Okay, so every time when you write out a chemical reaction, you should be able to write out the corresponding chemical equilibrium constant equation based on this. Okay, is that clear? Okay, any other questions? Okay, so recap quickly. Okay. First of all, every time you see a question showing this Kp, Kc, or equilibrium constant, you know it's chapter 12 questions for your midterm 1 for sure. Okay, so the things you should do is actually write out the chemical equations, right? And then write out the chemical quotient equations. Okay, so that's actually things I always do, right? So we see 3 examples. That's how I always do that. Then I start write out my ICE. Okay, then I read the questions again, right? To figure out, okay, they provide some numbers, right? Where I should put those numbers properly within that big box. Okay, and then I should always know only the number appear in the third row can be plugged into the equilibrium constant equation, right? I also need to know how to write out the changes, okay? Because in order to go from the initial all the way to your equilibrium, you should know how to write out the changes, okay? For your reactant, we always write negative X, right? For the product, we always write plus certain X, right? And then your initial plus they change will give you the equilibrium. Okay, and only the things show up in the equilibrium rule will be used to plug into the Kp or Kc to calculate your X. Okay, and then based on whatever the question is asking, okay, you should know how all this equilibrium pressure is related to your X to give out the final answer. Okay, so let's structure is the most difficult part of chapter 12. If you know these things 100%, then you should be actually have no problem solving all the questions in your homework and quiz. All right, so have that structure clearly in mind is most important thing for chapter 12. Okay, any question for this? Yeah, moving really fast today. That's good. Okay, so if there's no more question, we're going to go to the very last part of chapter 12. Okay, so very famous Le Chatelet principle. Okay, so this is actually a principle scientists use to predict where the reaction will move once you do some perturbation to your system. Okay, so the key is that the reaction, to understand this concept, okay, if you tie this concept to the equilibrium constant, okay, is that the reaction will move to the direction that maintain your KEQ, maintain your equilibrium constant. Okay, so what does that mean? I'll give you examples so you can see. Okay, let's say we have this chemical equation, 1A plus 2B, that give you 5C. All of them exist in the gas phase. Okay, so let's say that's the chemical equation that we have. So you should know that the Kp should equals to the pressure of C to the 5th power, pressure of A first power, pressure of B second power, right? So you should have no problem write out this. Okay. Then you will say, okay, the question will be something like this. If today, okay, let's say your system is actually already equilibrium. Okay, if today I increase the pressure of my C. Okay, meaning I dump more C into my system. Okay, into my container. Okay, predict the reaction is going to move to the reactant side or the product side. Reactant or product. Why? Okay, so the key idea is that there's only one constant here. What is that constant? Your KT, right? Remember I say from the very beginning of the lecture, I say, if you have a reaction, no matter what you do, at the end of the day, they will reach equilibrium. So equilibrium will be the destination. Okay, so think about this. When I say this guy is going to increase, that means your numerator is actually become bigger, right? Your K is a constant. It is not going to change. To make your K the same, that means actually you need to increase what? Your reactant, right? Therefore, you need to move to the reactant side. Okay, so everybody follow the things I just say? Okay, now we read the sentence I just wrote. Reaction will move to the direction that keep your KEQ the same or you maintain your KEQ. Okay, so that is actually the key of the Chateaubriand principle. Okay, the concept you should really have is actually your KEQ is always a constant. Okay, if I change certain things in my equations, the other term will need to change accordingly to make the K the same. Okay, so with that in mind, you should have no problem to predict whether the reaction is going to move. Is that clear? Okay, so let's do some more practice. Previously, I just say if I increase the pressure of C, right? Then I think everybody now can see that the reaction will move to the reactant side, right? If I increase the pressure of my A or B, then you know it will move to the product side. Okay, so that's actually the first simple question you're going to encounter. Okay, and things will get more complicated. Okay, because they can actually say something that's not very clear. Okay, for example, sometimes the reactions, so far we actually learned about this endothermic reaction and the exothermic reaction, right? Endothermic reaction means actually your reactant absorb heat that give you the product, right? Exothermic means actually your reactant interact, produce your product, and the heat that got released to your solution. Okay, that's actually another type of question you're going to encounter. Okay, when actually trying to use the Le Chatelier principle. For example, if today you have exothermic reaction, okay, so you need to learn how to translate that into the chemical equation. Okay, let's say if I'm at 1A plus 2B, they give me 5C is a exothermic reaction. Okay. Can you see that I should write in this way? Okay, so the heat will be produced, right? Exothermic means the heat will be produced. Therefore, I roll it on the product side, right? It's exothermic reaction. Okay. So that's actually the first thing you can do. You should know. Okay. Now the question will ask you something like this. If today I decrease my temperature, okay, so let me write it down. So if today I decrease my temperature, okay, predict the reaction will move to the reactant side or the product side. Okay, so you can think about when I decrease the temperature, okay, that means I'm taking away all the heat, right? But heat, based on the equation, right? If you look at the equation, the chemical equation, right? If you write out your K, of course you write the product over reactant, right? You can put the heat on your numerator, for example. Okay, if you decrease the temperature, means actually you lower down the heat. Okay, so under the case, what you're going to do is you're going to produce more heat to make your K the same. Okay, so this one is actually one that students always get confused. So the reaction will move to the product side. Okay. Of course, you can say on the flip side, right? Today I increase my temperature. In that in my system, I'm going to put more heat into my system, right? Then you should see that the reaction will move to the reactant side. Okay. Does everybody follow this? This part is actually most tricky conceptual things that I feel students always get lost. Okay. But it's the same thing, right? So main idea, your equilibrium constant has to be maintained. Okay. Are everybody fine with this? Okay. So I want to actually think a little bit deeper. Okay. If today we have endothermic reaction, then you should see that the chemical equation becomes this. Okay, so you should know the difference between exothermic and the endothermic. Okay, is that clear? Okay. Everybody understand this concept now because we're going to go to the example now. Okay, so this question says you have a reaction N2 plus 3H2 that give you 2NH3, which is exothermic as written. What will be the effect of the equilibrium position of removing N2? Okay, so the question actually asks you the reaction direction. The data you have is N2 plus 3H2. They give you 2NH3. And then this is exothermic, right? Therefore, you should put heat on the product side. Okay? And then you should also see that your K is going to be of course, all pressures, okay? So you know, let's say okay. Okay. So he says, if today I'm removing N2, right? That means the pressure of this guy, the pressure of your N2. So removing your N2 means the pressure of your N2 is going to decrease, right? And then to keep your K the same, since your P N2 is become smaller, right? That means your product need to actually decrease accordingly, right? And the way you make the product decrease is you move to the reactant side. Okay, so the answer will be the reaction will move to the okay. So that's actually how you figure out the answer. Any questions for this? If not, tell me. If I add in more H2, it will move to the product side. Okay. If I increase temperature, it will move to the reactant side. Okay. This will be actually one of the most confusing choice you're going to have in this chapter. If I add in catalyst, how will I actually change the reaction direction? How many of you will say the product side? Anyone say reactant side? See, the reason I say it's confusing is because students always think it will move to the product side. And that's not the correct answer. Okay, so what's the correct answer? What does catalyst do? Change the activation energy and only change the activation energy. That means the speed that you reach equilibrium will become faster. Okay, listen very carefully about what I'm saying. Okay, the speed to reach equilibrium will become faster. It does not change the equilibrium. Does that make sense? Yeah. So if you see this, okay, if you say if that in catalyst, how will it change the equilibrium position? The answer is no effects. Okay, and you should see that how easy student will choose move to the product side. Okay, so that's something that you need to actually clear distinction. Okay, you should know that the catalyst has nothing to do with the equilibrium position. Okay, only the concentration or the pressure or the temperature, only these three, okay, will change your equilibrium position. Is that clear? Okay, so there will be actually all the things that you need to know for chapter 12. Okay, not much, right? Pretty simple, right? So do you believe that you still have more than a week to prepare your midterm one? Okay, so far, how do you feel though? Good, or it's okay. You feel like it's not too difficult to follow, right? Can you believe that we fail so many students for the CHEM2 every year? Don't you feel insane? Okay, so I'm going to tell you why. Okay, since we have some time, right, I can actually, just randomly say something for 15 minutes. Okay, but I think it's going to be helpful for you. Okay, so the reason that student doesn't actually do well for this class is that they don't know how. Okay, I want you to think about the way I teach. Okay, every time you come to this lecture, okay, on day one, I tell you, follow my thoughts as much as you can, right? Did you see how I actually solve the problem? Did you feel like it looks like a piece of cake, right? If you follow the logic, it seems actually very straightforward to get to the answer, right? But late takes me decades to reach to this status, right? So think about you are the one who need to do these things from zero. How will it be possible with the effort you put in now? Okay, but can these things be learned? Yes, it can definitely be learned, right? But you need to really work with me first. Okay, if I ask you to watch the video, go watch the video. Push the button on your calculator, then do it. Okay, if you don't do it, then nothing will happen. Okay, so trying to think and trying to actually internalize how I think about things, how I actually approach the questions. Students typically did not read the questions carefully enough. Okay, every time students actually read the question, they keep trying to solve the questions without any framework in mind, right? And the end result of that is what? Students get so nervous, right? Every time you walk into a class, you see the question number one. Oh gosh, I forgot how to do this. Then what do? You get panic, right? I don't know what to do. I need to calm down. I need to calm down. But do you calm down? No, you don't, right? And then what's going to happen is actually after the exam, you'll come to my office, Dr. Chen, you know what? I'm a person who got nervous very easily, and that's what happened to my, situation when I walk into CASA. Okay, and how can I actually help you on that? There's nothing I can do for that specific situation. So no need to come to me if that's what happened to you. Okay, instead, what you should do is actually before the exam, come to me. Okay, I can explain things to you, and I'm willing to work with you. Right, so use your resource wisely. Okay, everybody's going to get busier and busier. Okay, once you get senior and senior. Okay, and you guys live in an era that's going to be super competitive. You're not just compete against human now, right? You want to become the super user of AI. Okay, so what's the things that AI cannot do that you have a chance to do? So I've been thinking about AI for a long time. Okay, because I'm so afraid that my job will be replaced by AI. Okay, so if I'm worried, I guess most students will actually worry too, because people always consider professors as something that's very difficult to be replaced, right? Then this time I feel like it's probably actually less possible for me to be replaced, because I realized that the reason human is special is simply because we have actually our own perspective. Okay, and those perspective, it won't be replicated by the AI easily. Okay, so the things we need to do is actually really make sure that the perspective that we're going to have in the future is unique. That's one. Second, is meaningful and important. Okay, so you should start to actually form your opinion. Okay, and trying to ask questions. Asking questions is something that's so important and will even be more important in the future. Because humans learn things slowly. Okay. Asking a good question is extremely difficult. Most of the question we ask is dumb, but that's okay. Yeah. Right? Because only after you practice that so many times, then you bring your own flavors into your questions. That's the things that make you unique. Okay. Every day you receive informations. In order to actually make yourself different, okay, you need to be more skeptical about the information you receive. Okay. So in the future will be information overflow. Okay. AI is going to generate a lot of informations. Okay. And those informations, I've been watching the content from AI for many years now. I start to see the content that generated by AI is all very similar. Okay, I cannot specifically tell you, okay, there are certain features, right? But when you read it, you have a feeling that, okay, this must actually coming from AI, and it's part of it coming from AI. Okay, but human is different. Okay? Everybody have your own flavors. Okay, so you need to actually start to think about, okay, what do you want to be? Okay, and work toward that direction. Okay, should you use AI tools now? Yes, definitely. It's not something you can escape. Okay, so don't avoid it. Okay, use that for your own good. Use that for your own interest. It's very important. Okay, but really start to think deeper. Okay, because the deeper than you think, then you will be more and more unique. Okay. I know you guys still very young, right? So most of you are freshmen. Yeah, so this actually still have time. That's good, right? So if don't sometimes the young generation have some misconcept about that you can achieve things quickly. Okay, they will never happen. Never. Okay, if it's something that you can achieve quickly, means everybody will be able to do that. Okay, but you can learn quickly. Okay, much faster than my generations. Okay, so right now, if you're just trying to read let's say a scientific manuscript, in my time, I may take a week to really understand the content. Right now, 20 seconds, it gives you a very nice summary, right? So tools actually improving quite a bit, okay? And you should use those things and then trying to internalize as much knowledge as you can, okay? And then in the future, unfortunately, you cannot only focus on one career, okay? You can actually just, like me, right? I'm chemistry major, right? So most of the professors, they spend all their life focus on either organic chemistry, inorganic chemistry, physical chemistry, right? So that was the mode that scientists want to have, or the society want to have in the past. Okay, so looking forward, the things they want to have, the person they want to have, is the person has multiple pillars. Okay, you have good understanding of multiple subjects. Okay, so you need to start to think about that. Okay, so what are the things that I can enjoy the most? Okay, and don't stick to one, stick to at least two. I think that will be actually very, very helpful when you're trying to find a job in the future. Okay, so use these things, use your AI tool wisely. Okay, talk to ChatGPT or Gemini. Okay, open. Okay, it's kind of fun, though, talking to them. Yeah, but if they keep agree with you with whatever you say, that's not right. Okay, so you can actually ask all this AI to become critical about what you say. Okay, you can actually change the setting over there. Okay, tell the AI, okay, I want you to be a critical thinker with me, yeah, and address my questions and criticize my points as much as you can. Okay, typically do a pretty good job to point out your weakness. Yeah, it's actually kind of fun doing that. Yeah, so you should actually try to do that and try to use the AI as much as you can. Okay. Yeah, but coming back to, I guess that's how I project. Okay, if I'm talking to my daughter, that's the same thing I would say to them. Okay. Yeah. Then the other thing that I want to talk a little bit more is that 5 minutes. Okay. So recently I got a lot more requests from students. Okay, which I believe is actually among the group here. Okay. About this undergraduate research. Should you do it? Okay. Short answer is yes, you should do it. Okay. But the bottom line is actually you should really know what you want to pursue after you graduate. Okay. So I'm being a professor who take undergraduate for years, undergraduate student for research for years. Okay. And all the students I take, they are, I think they are all biology related major, none of them is chemistry. Okay. And the student I take, I always ask them, okay, so what's the goal? What's the things you want to pursue for your future, right? Majority of them is either go to medical school, pharmacy school, what else? Optometry school. Yeah, it's all medical related or bio related. Yeah, none of them go to the chemistry, right? Yeah. And I tell them, okay, so if let's say your goal, right? Many of them, when they're trying to prepare to their futures, they listen to their colleagues, right? And their colleague will tell you, okay, do A, B, C, and D, right? Go to the volunteer in the hospital or in the pharmacy store, right? Think about this. Every year there are thousands of students trying to apply for the medical school. Everybody's doing similar things. Meaning doing those things is not going to make you look different. Okay, so what's the things will make you look different? Research experience. Okay, so if you are a student who has research experience, right? If you are a student who has a paper, you are golden. So should you actually do that? Yes, you should. Okay. The other thing is actually, what else can you actually look different? You should apply for all the fellowship at the UH. Okay, so you want to find a research lab that can help you do that. Okay, so to achieve goals, there are many things that you can do. Make sure the things you do is the relevant things. Otherwise, you're just wasting your time. Okay, so that's actually one thing that I think that everybody should know. Okay, the other thing I want to emphasize is the recommendation later, but I'm running out of time. So maybe next time when we have time, then we can actually talking about something outside the coursework. Okay, so I will stop here. Yeah, thank you.